Previously, in one of our sessions, when we were looking at properties of Laplace transforms, we looked at first shifting property. Now, in this session, we will look at second shifting property, but very quickly we will review the first shifting property once more. So, as per that, if Laplace of f of t is equal to capital F of s when s is greater than a, then Laplace of e to the power of a t f of t is equal to capital F of s minus a. Okay, that's what the first shifting property says. So in normal English, we have to write substituting s minus a for s in the transform means multiplying of the function f of t with e to the power of a. So let's very quickly prove this. We know capital F of s is equal to integral 0 to infinity of e to the power of minus st f of t dt. Yes, this is very clear to us. Now let's substitute s by s minus a. So 0 to infinity e to the power of minus, remember s we have to substitute it with s minus a t f of t dt. 0 to infinity of minus, no, not minus, e to the power of minus st times e to the power of minus into minus plus at f of t dt. Now, if you think about it, if we treat this as a single function, we can directly say this is nothing but Laplace of e to the power of at f of t as per Laplace definition. And on this side, remember, we have capital F of s minus a, which is what we had to prove. Laplace of e to the power of at ft is equal to f of s minus a. Now here, remember, we were substituting s by s minus a. So our focus was on s. Now in the second shifting property, we are going to shift our focus from s to t. So as per second shifting property, if Laplace of f of t is equal to capital F of s and g of t is equal to f of t minus a if t is greater than a. See, g of t is equal to this if t is greater than a, and it is 0 if t is less than a. If these two conditions are satisfied, then the Laplace of g of t is equal to e to the power of minus a s capital F of s. Okay, let's prove this. So let's begin with our g of t is equal to f of t minus a when t is less than, no, not less than, greater than a, and 0 when t is less than. Okay, now let's do the Laplace of g of t is equal to, as per the definition, 0 to infinity of e to the power of minus st g of t dt. Now, because it is a split function, greater than a and less than a, let's split this integral as well. So we'll split it from 0 to a and then a to infinity. So this becomes e to the power of minus st g of t dt plus integral a to infinity of e to the power of minus st g of t dt. Think of it like this. Here, when it is less than a. 0 to a means when it is less than a, g of t is 0. Yes. So that means this is 0. That means this whole integral is 0. And we are left with a to infinity of e to the power of minus st g of t dt. Of course, uh, here again, when it is from a to infinity, right? That means it is greater than a. T is greater than a. That means at that time it is e to the power of minus st f of t minus a dt, right? But we don't want it in terms of t minus a. So let's do some substitutions. Let's say z is equal to t minus a, which means t is equal to z plus, and if we differentiate it, we get dt is equal to dz. As far as boundaries are concerned, when t is equal to a, z is equal to 0, and when t is equal to infinity, z will also be equal to infinity. Okay. So now let's do the substitutions. This is what Laplace of g of t. So let's write that Laplace of g of t is equal to 0. Remember, when it is a, z will be 0. When it is infinity, this will be infinity. So this also becomes infinity. So 0 to infinity of e to the power of minus s. T is what? T is z plus a. So z plus a. F of t minus a. T minus a is z. So f of z. And tz, dt is dz. Okay, now we can simplify this. Let's split it off. Minus e to the power of minus sz times e to the power of minus sa, f of z dz. Okay. Now here remember dz. So we are in the z world. So which means here e to the power of minus sa, there is no z. So this ends up being a constant. So we can take it out. Minus sa integral 0 to infinity of e to the power of minus sz f of z bz. And as per the Laplace definition, this is nothing but the Laplace. So e to the power of minus sa Laplace of f of z. And let's substitute back z. So minus sa Laplace of f of z is what? T minus a. T minus, so Laplace of g of t is equal to e to the power of minus sa times Laplace of f of t minus a, which is what we had to prove. Actually, we can write one more step, e to the power of minus sa, and this can be written as capital F of s. And in general, we can say Laplace of g of t is equal to e to the power of minus sa capital F of s, which is what we had to prove. Now, another way that this can be looked at, this is one way. Another way in which we could have started off is if Laplace of f of t is equal to capital F of s, and f of t minus a times g of t minus a is equal to 0 if t is less than a. F of t minus a if t is greater than a. That is true. Then Laplace of f of t minus a times g of t minus a is equal to e to the power of minus a s capital F of s. Let's actually prove it this way as well. So let's begin with the left hand side. Laplace of f of t minus a times g of t minus a is equal to integral of 0 to infinity of e to the power of minus st f of t minus a g of t minus a dt. This is based on the Laplace definition. Okay, because it is a split function, we can split this integral. So we can write it as 0 to a e to the power of minus st f of t minus a times g of t minus a dt plus a to infinity e to the power of minus st f of t minus a g of t minus a dt. Okay, now in the first case what happens, this is 0. Yes, this will be 0 if t is less than a. So here it is less than a, so that means the integral also becomes 0 plus, and here what is it, f of t minus a times g of t minus a is nothing but f of t minus a. So which means this can be written as a of a to infinity of e to the power of minus st, and then what, this becomes f of t minus a. Remember here the product of this is f of t minus a itself if t is greater than or equal to a, and here it is greater than. Okay, now let's substitute, do some substitutions. So let us say z is equal to t minus a. That means t is equal to z plus a. And if we differentiate, we get dt is equal to dz. Again, as before, if t is equal to a, then z is equal to 0. When t is equal to a, z is equal to 0. And when t is equal to infinity, z is equal to infinity. So if we do the substitutions, we get Laplace of f of t minus a times g of t minus a is equal to integral. Remember, when t is equal to a, z will be 0. So 0 to infinity of e to the power of minus s, and t is z plus a. F of t minus a is z, dt is dz. 0 to infinity of e to the power of minus sz times e to the power of minus sa f of z dz. And pretty straightforward. Now this is a constant, there is no z involved here, so we can take it out. Minus sa integral 0 to infinity of e to the power of minus sz f of z dz. Now as we know, this is nothing but Laplace of f of z, and let's substitute back e to the power of minus sa times Laplace of f of t minus a, or what we could also do is e to the power of minus sa capital F of s. Right? Now remember, whenever you have this type of a situation where you have a Laplace of something equal to something, then we can say that Laplace inverse of e to the power of minus sa or as capital F of s is equal to inverse Laplace of Laplace will cancel out. So we are left with f of t minus a g of t minus a. So if you know one, you know the other. So that is the second shifting property. Okay, that's it for now. Bye.